So now you could speculate that indeed the reason that a particle may have a magnetic moment if it's made by a little ball of charge that is rotating. But that was exactly what Pauli didn't like, of course. And you would like to see what's really happening with particles. So when you think of a true quantum mechanical particle, let's think of a particle in general, a solid particle rotating. We'll change the name L to S for spin angular momentum, because that little part, this is just one particle. We're not thinking of that little particle going around a nucleus. We're thinking of that little particle rotating. So this is a little piece of that little particle that is rotating. So you could ask if for the electron, for example, the electron, for example, is it true that mu is equal to E over 2 mass of the electron times its spin? So this would be a vindication of this classical analysis. It might be that it's related in this way. So actually, it's not quite true, but let's still improve this a little bit. In terms of units, we like to put an h bar here and a 2me, and put spin here, angular momentum, divided by h. Because this has no units, h bar has the units of angular momentum, x times p. It's the same unit, so units of angular momentum, so h bar would be convenient, so that over here you would have units of a dipole moment or magnetic moment. Magnetic moment units. So what does happen for the electron? Well, it's almost true, but not quite. In fact, what you get is that you need a fudge factor. The fudge factor is that actually, for elementary particles, you have a g, which is a constant, which is the fudge factor, eh bar 2 over m of the particle, s over h bar. Sometimes called the Lande factor. You must put a number there. Now, the good thing is that the number sometimes can be calculated and predicted. So when people did this, they figured out that for the electron, the number is actually a 2. So for the electron, g of the electron is equal to 2. Now that, you would say, cannot be an accident. It's twice what you would predict sort of classically. And the Dirac equation, the relativistic equation of the electron that you have not studied yet, but you will study soon, predicts this g equal 2. It was considered a great success that that equation gave the right answer, that people understood that this number was going to be 2. So for the electron, this is 2. So this quantity is a magnetic dipole moment, is called mu b for Bohr magneton. So how big is a mu b? Is about 9.3 times 10 to the minus 24 joules per Tesla. Yes?
So where exactly
Right. So the classical analysis is not valid. So it's pretty invalid, in fact. You see, the picture of an electron as of today is that it's a point particle. And a point particle literally means no size. The electron is not a little ball of charge. Otherwise, it would have parts. So the electron is a point particle. Therefore, a point particle cannot be rotating and have a spin. So how does the electron manage to have spin? That you can't answer in physics. It just has it. Just like a point particle that has no size can have mass. How do you have mass if you have no size? You get accustomed to the idea. The mathematics says it's possible. You don't run into trouble. So this particle has no size, but it has an angular spin, angular momentum, as if it would be rotating. But it's definitely not the case that it's rotating. And therefore, this too confirms that it was a pointless idea to believe that it would be true. Nevertheless, kind of unit analysis or maybe some truth to the fact that quantum mechanics changes classical mechanics turns out that it's closely related. For the proton, for example, the magnetic moment of the proton is quite complicated as well, because the proton is made out of quarks that are rotating inside, and how do you get the spin of the proton and the magnetic moment of the proton is complicated. The neutron that has no charge has a magnetic moment because somehow the quarks inside arrange in a way that their angular momentum doesn't quite cancel. So, for example, the value for a neutron, I believe, is minus 2.78 or something like that. It's a strange number. Another thing that is sort of interesting, that it's also true, is that this mass is the mass of a particle. So if you're talking about the magnetic moment of the proton or the neutron, it's suppressed with respect to the one of the electron. The electron one is much bigger because actually the mass shows up here. So for a neutron or a proton, the magnetic moment is much, much smaller. So in fact, for an electron then, you would have the following. Mu is equal minus g, which is 2, mu b, S bar over h. And actually, we put a minus sign because the electron has negative charge. So the magnetic moment actually points opposite. This was with, if you rotate this way, the angular momentum is always up. But if you rotate this way and you're negative, it's as if the current goes in the other direction. So this is due to the fact that the electron is negatively charged. And that's the final expression.